When you're considering a sample of a gas, there are four characteristics that are important to look at. Those are pressure, which is abbreviated with a capital P, volume, which is notated with a capital V, the number of moles of gas in that sample, which is notated with a lowercase n, and the temperature of that gas, which is notated with a capital T. But you have to remember, when you're dealing with gases, the temperature has to be in kelvins. So the first relationship between these characteristics, though, that I want to talk about is pressure and volume relationship. So let's say you have a balloon, and I'll just draw a circle for my balloon. If I were to increase the pressure on this balloon, maybe by some outside force, and I begin exerting pressure inward on this balloon, think about what that would do to the balloon's volume. If I started pressing on a balloon from all sides, I'm going to restrict the space that that balloon has. So as this pressure increases and there's a pushing on this balloon, what will wind up happening is the volume of that balloon is going to shrink. As the pressure exerted on this gas increases, the volume of the gas decreased. Let's consider another way of thinking about this. Maybe if you had a piston in a car. Okay, so this piston is pushing down on this sample of gas. Okay, so this top part of this piston can move up or it can move down. And it's pressing on this gas with a certain pressure. If I were to push with less pressure of this piston, so what this would look like is if this piston is now not pushing as hard, what's going to happen is this sample of the gas in here is going to then be able to expand and push that piston up. So as the pressure of this piston decreases, this gas is then able to expand and the volume of it will increase. So as the pressure decreases, the volume increases. You could also consider, for example, a weather balloon or even just a regular balloon. As you release the balloon up into the atmosphere, as it moves further into the atmosphere, the pressure exerted on that balloon decreases. And ultimately, what will happen is since the pressure is decreased, the volume of that gas will increase until that balloon fails. So really what we've just described is a situation where when pressure goes up, volume goes down. If pressure goes down, volume goes up. If the volume goes up, the pressure must have gone down, and if the volume goes down, the pressure must have gone up. Now, this is assuming nothing else about this gas changes, but the pressure to volume relationship is inversely proportional. As one increases, the other is decreasing. So for that reason, it is fair for us to say that the pressure times the volume has to equal a constant. And since that's constant, if I were to consider the initial pressure of a gas times the initial volume of the gas, it would have to equal the new pressure of that gas times the new volume of that gas. This is just a mathematical way of representing the inversely proportional relationship of pressure and volume. The next relationship is the volume-temperature relationship. And again, this is assuming nothing else changes. So in this situation, volume and temperature can change, but pressure and the moles of gas can't. So consider you've got a balloon with the sample of a gas in it. But then you heat that balloon on a fire. There's my very lovely fire. Well, think about what the kinetic molecular theory has to say here. As these particles' temperature increases, their kinetic energy is increasing, which means their velocity is increasing. These particles are going to be moving at a greater rate, so when they hit the sides of this balloon, it's going to force this balloon to swell in order to maintain the pressure, which we had said earlier has to be constant in this situation. So in order to maintain that pressure, the volume of this balloon has to expand. We have the same amount of gas, But what has happened is because they've heated up, they have more kinetic energy, the particles are able to spread out further, which means the volume will increase. So what we've just deduced then is as temperature increases, volume increases. If temperature decreases, then volume must decrease. If you've never gotten a balloon and blown it up and stuck it in a freezer, 10 out of 10 recommend. It's pretty neat to see what happens. That balloon, since the temperature decreased, the volume will decrease as well. Now, on the other hand, if the volume were to increase and everything else is constant, that means the temperature must have increased. And same the other direction. If the volume decreases, the temperature must decrease. These are directly proportional to one another. And for that reason, we can mathematically say that if you took the initial volume and divided it by the initial temperature, this ratio has to be maintained. So the initial volume divided by the initial temperature has to equal the second volume divided by the second temperature. Or you could have written it as the initial temperature over the initial volume must equal the final temperature divided by the final volume. Either way, they're representing the same thing. Since these are directly proportional, if the temperature in Kelvin doubles, then the volume must double to maintain that proportion, which is what allows us to write these equations. So the volume-moles relationship is very similar as well. Think about a balloon again. If I have a balloon and it has, I'll draw 5 particles to represent 5 moles of gas, and then you introduce more moles of gas, such as just blowing more air into the balloon, if the pressure and the temperature are constant and the only thing changing are the volume and the moles, then if you put more air into a balloon, it's going to have to occupy a larger volume. So this balloon on the left only had 5 moles of gas, whereas this balloon on the right has 10 moles of gas. To offset that increase in the number of moles, the volume had to increase as well. So what that leads us to are these equations, where if you increase the number of moles in a sample and nothing else changes in regards to the pressure or temperature, then the volume has to increase. If you decrease the number of moles, in other words, you're letting air out, a gas out, then it only makes sense for the volume to go down. And again, if the pressure and temperature are constant. If the volume increased, then the moles must have increased. If the volume decreased, the moles must have decreased. Which leads us to recognize that this also is a direct proportion. These two variables are directly proportional. So it makes sense for our equations to reflect the previous equations where they were directly proportional, in that we can say the initial volume divided by the initial number of moles has to equal the new volume divided by the new number of moles, or the initial number of moles divided by the initial volume has to equal the new number of moles divided by the new volume. And the last relationship we're going to look at is the pressure-temperature relationship. And again, this assumes the other two variables don't change. So if the number of moles and the volume are constant, then what we're about to say about the pressure-temperature relationship is true. So let's say that you have a vessel, like a metal vessel. This means that the volume of it cannot change. So if there's 1 mole of a gas in here, and then let's say that we heat this container up. Okay, we put it on a fire. Well, the kinetic molecular theory once again says that as you increase the temperature, you increase the kinetic energy of these particles, meaning they're going to be traveling faster, which means they will collide with the walls more often and more forcefully, meaning the pressure has to increase. As the temperature goes up, those particles hit the wall more often and with greater strength, so the pressure has to increase. So that leads us to these conclusions then. As temperature increases, pressure increases. As temperature decreases, pressure must decrease. And then thinking about this backwards tends to be a struggle for some people. But if you increase the pressure while maintaining the number of moles and the volume, the temperature has to increase. Or if you decrease the pressure, you are decreasing the temperature. An example here would be a can of compressed air, maybe like keyboard cleaner. If you spray that can and release that air for a long period of time, as the pressure is decreasing, the temperature of that can decreases as well. And that's why sometimes those compressed cans of air feel cold after you've used them for a while. So again, this is one more directly proportional relationship. So again, it makes sense that our equations then read the initial pressure divided by the initial temperature in Kelvin has to equal the second pressure divided by the second temperature, or the initial temperature divided by the initial pressure has to equal the second temperature divided by the second pressure. Now you can actually combine all of these equations into one, in which case you can say that the initial pressure times the initial volume divided by the number of moles initially times the temperature in Kelvin initially has to equal the second pressure times the second volume over the second number of moles times the second temperature. Since these are all proportional to one another, some inversely, some directly, you can relate them to this one equation. And you can even take it a step further. Since this information on the left has to equal this information on the right, anytime you take a pressure times a volume, divide it by a number of moles, and divide it by a temperature, it has to equal a constant. That constant in this case is R, which is 0.0821 if and only if your volume is measured in liters, your temperature is measured in Kelvin, and your pressure is measured in atmospheres. And these are the most common ways to measure these. So for this reason, this value of R, which is called the ideal gas constant, it's best to memorize that the ideal gas constant is 0.0821, but you have to understand that that means your volume must be in liters, your temperature must be in kelvins, and your pressure must be in atmospheres. So if PV over NT equals this R, since nobody likes fractions, let's multiply both sides by NT. That will lead us to PV equals nRT, which is the most important law when you're dealing with gases. This is called the ideal gas law. And this one equation can relate all four of the characteristics of gases into one. So something interesting to think about is that you can actually relate the density of a gas into this ideal gas law. So if PV equals nRT, well, if we think about what the number of moles really means, maybe we should outline this in blue. If the number of moles, in order to calculate the number of moles, you could take your mass of your substance divided by its molar mass, and that would tell you how many moles of that substance you have. For example, if you have 64 grams of oxygen, its molar mass is 32 grams per mole, you have 2 moles of oxygen. Well, since moles is nothing more than mass divided by molar mass, let's rewrite this. Let's say PV equals mass of the gas times RT divided by that gas's molar mass, which I'll notate with 2 capital M's. All we did here was replace N with mass over molar mass, which is the same thing. Now, even more interestingly, if we were to divide both sides by the volume in order to get pressure by itself, this left side would equal pressure, but then I need you to consider what is mass, which is on top of this fraction, and we're now dividing that by volume. Well, mass divided by volume is nothing more than density. So now you can replace mass divided by volume with density. So the density of a gas times R times T divided by that volume, and you can relate density of a gas to the pressure of a gas. I'm sorry, I actually just left that volume on there. What was I thinking here? We replaced mass and volume with density. So let's do this part again. Sorry about that. I would restart, but I'm not about to restart a 16-minute video. So again, the pressure, we took our mass here and divided it by volume, resulting in density, which is still multiplied by R and T. However, instead of volume going on bottom, the volume is gone because mass divided by volume is density. You're left with molar mass on the bottom. That makes way more sense. So then it is possible to rearrange this equation to solve for density. So let's get us some space here. So to solve for density, I'll multiply both sides by molar mass. So that leaves me with the density times R times T equals the molar mass times the pressure. Divide both sides by RT. And the density of a gas is equal to its molar mass times its pressure divided by RT. Now, you don't have to necessarily memorize this, but I have a very eloquent way of memorizing that density equals molar mass times pressure over RT. And that is to say that, dude, my Pringles on top, you know, the delicious chip, totally rotted. Totally rotted. And this has absolutely nothing to do with density. It's just my mnemonic device that density equals molar mass times the pressure divided by RT. Dude, my Pringles totally rotted. And this has been all of the very exciting gas laws.